G'day, in this video we're going to be looking at some techniques that we can use to determine the position of a projectile as it moves through the air. Again, we're going to be looking at dot points 5.1.1, 2, and 4. We're going to be continuing to apply concepts which focus on the horizontal and vertical components of a projectile's velocity and using our assumptions about acceleration in both of those directions in order to be able to calculate or determine the position of a projectile. So some key learning intentions. We're going to be applying those basic projectile motion principles, all about horizontal and vertical acceleration. But today we're going to be looking at the S equals ut plus half at equation. Once we've had a look at applying these concepts to the equation, we will practice using that in a calculation. So when we are applying our concepts of horizontal acceleration to displacement, again, air resistance, tailwind, or some other applied force could all influence horizontal acceleration, but we assume that none of those factors are applying. If they were, especially air resistance, we would expect the projectile to fall shorter than it actually will in our calculations, where we assume the trajectory is a complete parabola. So as a result, in our kinematic calculations, we assume that AX is equal to 0. Applying that to S equals ut plus a half at squared, this is going to again cancel out the second term in the right-hand side of the equation and leave us with Sx, the displacement in the x direction, is simply equal to ux times t. Similar to what we did with v in the previous video, we can calculate the displacement in the x direction for the projectile at any given time. When we look at applying vertical acceleration to this displacement concept, again, the only acceleration that the object will be experiencing in the y direction is gravity. And we assume that the acceleration due to gravity is equal to negative 9.8 meters per second, meaning that we can essentially substitute this value in where a goes in the s plus ut equals a half at squared formula. What this means then is that Sy is equal to Uyt plus a half Ayt squared, could also be written as half Gt squared. So to keep things consistent, we'll apply this concept to our running example that we've been working with. We're throwing a ball, launch angle of 48 degrees, velocity of 25 meters per second. In this question, we're being asked to determine the horizontal and vertical displacement of the ball at 2.5 and 5 seconds after the ball was thrown. So again, we've got some working on the side that allow us to determine ux and uy by breaking up the u vector into horizontal and vertical components. Using this information, we can calculate then for displacement at the two times given. It's also really important to first identify a couple of key pieces of data. First off, we'll need to use g, which is equal to negative 9.8 meters per second squared. Ux is equal to approximately 17 meters per second. Again, if we need to substitute in this value to any of our equations, we're going to substitute in the actual value. Hopefully you've got that saved in your calculator. If not, you just have to actually apply the formula again really quickly to get that number with no rounding in it. And as well, we have uy, which is about 19 meters per second. So first off, I want to do some calculations for when t is equal to 2.5 seconds. So the two core formula that we're going to apply is that Sx is equal to uxt and that Sy is equal to uyt plus half Ayt square. So the displacement in the x direction, where t is equal to 2.5 seconds, is going to be equal to our ux, which is about 17, times our t, which is 2.5. This should come out to 41 meters to two significant figures. When we then apply this to our y direction, we should be able to find that Sy at t equals 2.5 seconds is equal to our uy, which is about 19, times t, which is 2.5, plus half g, which is negative 9.8 meters per second squared, times t squared, which is 2.5 square. When we put this in our calculator, this should come out to about 15.8 meters, which is 16 meters to two significant figures. Now in this question, there's two parts. We're also asked about the displacement after 5 seconds. So here we're going to look at what happens when t is equal to 5.0 seconds. To solve, we're going to be using the same formula, that Sx is equal to Ux t, and that Sy is equal to Uyt plus a half Ayt square. So the x calculation is quite simple. The displacement in the x direction for t is equal to 5 seconds is going to be equal to 17 times 5, which should come out to about 84 meters to two significant figures. However, the y component is going to be a little bit more tricky and it's going to come out with a bit of a funky answer. So let's calculate first the displacement in the y direction for t is equal to 5 seconds is going to be equal to 19 times 5 plus a half g, which is negative 9.8 meters per second square, times our t square, which is 5 square. Now this comes out with a negative number, which is negative 29.6 meters. Now this number is not desirable and it actually has some implications for this problem. Now if we have a displacement in the y direction which is less than 0. Now what this implies is that as the projectile has gone through all of its pathway and its trajectory, that the projectile has then continued to move below where the object was initially launched. Now if the object was launched at the ground, what that means is the object has gone underground. In a realistic sense, this isn't really possible. What this suggests is that 5 seconds is greater than the time of flight. And therefore, as a result, these two displacements are not legitimate, as the projectile will never actually get to these positions at all. This concept is something that we will look at in further detail in class. Thank you very much, everyone. In the next video, we're going to be looking at a few other things that we can calculate using some simple projectile motion techniques. We'll focus on calculating for the actual time of flight, as well as the maximum height the projectile achieves, as well as the final velocity of a projectile. But until then, have a good one.